Log on, tune in, find out. Another good idea from Cambridge.
The second semester morning session, Lehrer from Sydney will talk to us about non-commutative invariant theory. Yes?
I'd like to also begin by thanking the organizers for giving me this opportunity, this wonderful conference, and also I second my thanks for their efforts with regard to the weather, and I want to thank them for yet another thing which nobody else has mentioned, but they have actually chosen the first week of Wimbledon for this meeting and not the second week, for which I'm very grateful. I want to talk about some results in non-commutative invariant theory. That means invariance of quantum group actions. This is a subject which has been touched on implicitly by several speakers here and has a large literature. It's often very difficult, like with classical invariant theory, to gather the strands and get a clear thread. So I want to start by just a couple of remarks about classical invariant theory. Which, before I started thinking about this, I thought I understood well. I'm not quite so sure anymore. So let's take G, a complex reductive group, and V, a simple G module. There are three contexts for classical invariant theory. The first one is that you take a tensor power of V and you try to describe what are the endomorphisms of this tensor power which commute with the G action. So this way of looking at invariant theory is often called Schur-Weil duality. I think it should also have the word Brouwer in it. Second way of approaching the subject, which is throughout the literature, is to look at the space of multilinear functions or on some large direct sum. This should be a different, let me put a K here. So one looks at multilinear functions from this or equivalently linear functions on the tensor product, and one wants to know what are the functions which are constant on G orbits. And the third way of looking at classical invariant theory is to look at the G module, V tensor to the K, tensor V star, tensor to the L, take its coordinate ring and ask what are the G invariant functions, what are the G invariant polynomial functions on this space. Pardon?
You want tensor products and direct sums.
Direct sums. I do want direct sums. Sorry. That's exactly why I wrote it in this way there. So So what I want to point out is that, of course, in the classical case, it's a straightforward thing to move between these. The language may be different, but there are equivalences among these problems which are pretty obvious. And the two fundamental questions one asks in each case are what are generators for the invariant and what are the relations among those generators. But those words mean different things in each of the three different contexts. So generators in this case means generator. Here we are dealing with a non-commutative associative algebra. Here we're dealing with linear generators and linear relations. Here we're dealing with commutative algebra, and we're asking for commutative algebra generators and relations among those. In the quantum case, the equivalence among these three ways of looking at things are not as straightforward, which makes the subject more interesting. And the particular way that I'm going to approach the quantum case is by looking at this third way of talking about invariant theory. Let me, before leaving the classical case, just point out that these problems have only been solved for a very small number of modules or pairs GV. And those are the ones that I'll focus on in the quantum case as well. Essentially, not much more than the natural modules and their duals for the classical groups are understood. G2 is the only other case for which it might be said there's a reasonable understanding. And for those who think that everything is known about this, let me just mention that even in the very first Schur-Weil Brouwer way of looking at this, if you take for V the natural module for ON, it's known that the Brouwer diagrams generate all the endomorphisms here. This was proved by Brouwer in 1937. But the question of all relations among the Brouwer diagrams is really unsolved as a problem in algebra. In other words, the kernel of the surjective homomorphism to this space from the Brouwer algebra is not described in terms of the generators and of the Brouwer algebra. And there's a very good reason for that, because the Brouwer algebra in general is not semi-simple. So although we're in a semi-simple situation, we have a map from a non-semi-simple algebra to a semi-simple one, and the kernel of that map is not so easy to describe. So, let me give a little bit of quantum background. So corresponding to G, we have a Lie algebra written like that. This Lie algebra has a universal enveloping algebra, and this has a non-commutative deformation, which I'll write as UQ of G, and I'll often just write UQ when the context is known. This process is not commutative, and I think I didn't start with the right one, did I? So UQ is generated. I'm going to adopt the same conventions as John Brunden did. And I've got to just remind you what they are, because it might become relevant later. So there are relations which I'm sure everyone in this room knows, and the convention that I'm going to use is that this is EI tensor KI plus 1 tensor KI inverse, 1 tensor KI rather. And for consistency, pardon? Oh, pardon? Sorry, KI tensor 1, isn't it? Pardon? Oh, yes, sorry, yes. What am I doing here? Is that right? Okay, let's hope I get this one, do better with this one. Okay, so this is the antipode, which is important in the context of invariant theory because one is often dualizing. So the category of modules that I'll be working in is CQ. These are locally finite, mostly actually finite dimensional, but in any case always locally finite, UQ modules of type 1, 1, 1. That means that they are direct sums of weight spaces, and I'll just point out what it means to be a weight vector. So V in a module V, this is a UQ module, has weight lambda in P, where P is the weight lattice. If KIV is equal to Q to the alpha I lambda times V. So that's the category I'm going to work in. This is a tensor category, as is well known, and moreover, it has a braiding. And this braiding is provided by the R matrix. So we have a universal R matrix, which can be thought of as an element of some completion of UQ, tensor UQ. It satisfies celebrated Yang-Baxter relations, which I'm not going to write down, but there are two properties of R which I want to record, which will be important for our context, and those are that if you have two modules, A and B, then you can form their tensor product, and we have the reversal map that takes A tensor B to B tensor A. This is not a UQ map, but if we compose it with R, then what we get is something which does respect the UQ action. So this is in HOM UQ A tensor B to B tensor A. And so that's the first thing, the first property, which will of course be crucial. And the second one is that if we have three modules, then this operator applied to the first pair is called R1, and the corresponding operator applied to the second pair is called R2, and with that convention we have the celebrated braid relation. And so in particular, if we take any module V in CQ, I should have said actually that this is all over the field. I'm treating here the generic case, the field K. I'll write it as K, which is C of Q to the half. It's a function field. So if I take a module, then I take a tensor power of this module, and I wish to look at the endomorphisms which commute with UQ. Well, one thing that I always have is this. I have these this R1, this PR is often denoted by R check. I'll denote this by R check. So what I have here is a map from K, from the group ring of the R here. Oh no, I'll take N. Of the N-string braid group, where the braid generators are mapped to R check for the I plus 1 factors in that tensor. Okay, now we want to work with an analog of the third problem. In other words, we want to get into the world of quantum coordinate rings. So there are two constructions. I'm going to combine two known constructions. One is a UQ. It's actually written in the literature as module algebra. These are discussed by Montgomery in her book, Brown and Good-Earl. Not in exactly, their treatment is actually different from what I'm going to talk about. So we say that we take an associative K algebra. So I'll sometimes leave out the module algebra, so I'll just say UQ algebra. So this is a UQ, I'll put in module this time, module algebra if, first of all, it has to be obviously a UQ module and locally finite. We require it to be locally finite and of type 111, so it's in CQ. And secondly, UQ has to respect the algebra operation, the respects multiplication in A. So what that means is you can express this as a diagram, or you could write it like this. So if you have an element of U, and you take a product of two elements of A, then that's a sum of x1f times x2f to x2g, where delta of x, delta of U rather, is equal to sum of x1 tensor x2. So that's what preservation of the algebra structure means. Now, one of the tricky points of this subject is that naive constructions of coordinate rings of even affine space aren't flat. And to get around that, we work with a tensor product of such algebras, but such a tensor product is not all that easy to construct. But let me just point out two facts about A. The first one is that if A is commutative, then it's trivial as a UQ module. In other words, this is intrinsically a non-commutative subject. The second thing is that it's easy to see that the invariants, that means the space of points of A on which UQ acts according to its trivial representation, is a subalgebra. Now, even though the action of UQ on the invariants is of course trivial, this is often a non-commutative subalgebra itself. Even the invariants form a non-commutative subalgebra. In fact, in every significant case that we'll be looking at, that is the case. So we want to make the category of such algebras into a tensor category. So it's not hard to see that there's an obvious structure. If you have two such algebras, A and B, there's an obvious structure of algebra on the tensor product, but that structure is not preserved by UQ. So in other words, you don't get a UQ module algebra by just naively taking the tensor product of two such things. So what we do is we define this multiplication as follows. Instead of naively multiplying component by component, you first of all apply R check here, and you apply R check to the middle. You take the identity of A, and R check, and then the identity of B, and that gets you to A, tensor B, and then you go to here via multiplication in A and the multiplication in B. So you have this twisted multiplication. This is not a new thing. This appears in the literature. I think it's actually in it's mentioned in one of John Brunden's papers. And the main point is that with this multiplication, A tensor B is a UQ algebra. So there are two other remarks. This statement means that this is associative, which is not completely obvious. It needs to be checked. And the multiplication is preserved by UQ. And another thing is that this operation is associative. In other words, there's a canonical isomorphism between A tensor B tensor C and the other bracket. Okay, now this gives us somehow new UQ algebras from old ones, but we need something to get started to do our invariants. So those are the quantum symmetric algebras. So I start with V, a finite dimensional UQ module, something like an analog of the natural representation of one of the classical Lie algebras. And I wanted to have the property that V tensor V splits is multiplicity free. This is satisfied by most of the. Then R check is an endomorphism. It defines an endomorphism of V tensor V. So it acts as a constant on these simple components. And that constant is a sign times Q to a certain power. Let me call it P1, and in general it'll be epsilon I Q to the Pi. This sign is actually exactly the same sign as the involution, the position changing involution acts by when you take the classical limit of this module at Q equals 1 and go to the classical case. So there's a very obvious definition which several authors have used. I think actually the idea to use this might go back to Kazhdan some time ago, but certainly Berenstein and Zwicknagel have used this construction and written a lot about it. What one does is one takes the tensor algebra of V and one takes the ideal which is generated by the sum of the Li such that epsilon I is -1. So this would, in the classical case, just be the exterior, the alternating tensors of degree 2. So this in the quantum case, we just take the Q analog of this, and we call this SQ of V. I hope that didn't cause any terrible problems. Now, just to give you a feel for what's happening here, in the case of SL2 and the natural representation, you get simply this is isomorphic to the free algebra on two variables, say xy, where xy is equal to Q inverse times yx. It's a quantum plane, you could say. So, in general, I can see the time is going a little faster than I thought. I'm going to show you all that many examples, but the main property which we require to get significant results here is flatness. So SQ is flat if it's a graded thing. So it's flat if the dimension of its graded components are the same as what you get when you put Q equal to 1. So there are many ways to say that, but I'll just abbreviate it by saying the limit as Q goes to 1 of SQV is just a symmetric algebra. And regrettably, this property of flatness is not very common. So examples, the natural modules for SLN, ON, SP2N, and that is about it. For SL2, Berenstein and Zwicknagel showed that the only flat cases are the simple modules of dimension 1, 2, and 3. Now 3, of course, is the case of SO3. So that's not that also falls into these. The problem seems to be that if there are too many of those, the R matrices act with many eigenvalues, and the algebra of endomorphisms is very complicated. In SL2, for example, this map, which I wrote down here, from the braid group to the endomorphisms, is surjective for every irreducible representation of UQ of SL2. But that is not enough for this property of flatness. This flatness is an elusive thing. So then, if we, so what we then do is define if pardon? It is correct. Yeah, it's true. Yeah, but those standard modules all have the property that the R matrix acts with at most 3 eigenvalues, of which either 1 or 2 might be negative. So it can. There are different. So if V and W are flat, then you define SQ of V plus W I should really say, yeah, okay, I'll write SQ V plus W is SQ of V tensor SQ of W. So this is how we deal with the general sums of the type that I mentioned in my introduction. It just occurred to me that I didn't mention that everything I'm talking about is joint work with two colleagues. This is joint work with Ruben Zhang from Sydney and Hechun Zhang from Tsinghua. No relation. Not related to me either. Okay, so I had some examples which I don't think I've got time to do. I think with the PowerPoint you can do it, but not with a hand lecture. So what I'm going to do next is give you some sample theorems and a flavor of how to prove them, and then indicate an application. The application is to the equivariant K-theory of quantum vector bundles, because that type of thing is expressed in terms of finitely generated, the category of finitely generated modules. And one of the issues that has to be addressed in this quantum setting is whether these algebras of invariants are finitely generated. So let's take the case of ON, and I'll make it O2n just to be definite. There's really not much difference. It's only in the vocabulary that there's a difference. So the natural, so we take UQ to be UQ of SO2n in this case. So the natural module has a basis Vi, let's say, where I is plus or minus 1 up to plus or minus n, and the weight of EI, the weight of VI rather, is epsilon I, the ith fundamental weight, and it's either plus or minus this depending on I divided by I. I guess this is one way to express it. So V minus 1 has got weight minus of epsilon 1. So here we have a root system of type Dn. The natural module is, of course, L epsilon 1, and its square is the trivial module plus L2 epsilon 1 plus L epsilon 1 plus epsilon 2. And there is an obvious invariant. This is a one-dimensional space, and it is spanned by a certain element which I'll call phi tilde, which is the sum of q to the n minus k, k equals 1 up to n, v k tensor v minus k plus q to the k minus n, v minus k tensor vk. And this element is something like the quantum truth. This is in the V tensor squared, which is isomorphic to its dual. So it's something like a quantum trace. It's something like actually a square root of a quantum trace. And I want phi to be the image of phi tilde under the map eta from T of V to SQ of V. The SQ is this quantum symmetric algebra. So the first observation about this case is that there are very easy things that you can prove about this. That phi is actually in the center of SQ of V, and of course it's invariant because it's already invariant as a tensor. So SQV to the UQ, and in fact in this small, just in this tensor square, SQ of V to the UQ is nothing but the ring of polynomials. It's just the polynomials in phi. This is exactly analogous to the classical case. And let me, as an aside, I don't think I'm going to have time to talk about quantum vector. Oh, I've got a little bit longer than. When am I supposed to finish? 10 past. Okay, all right. So I still don't think I'll get to quantum vector bundles, but let me mention that this gives you the opportunity. So this is a sort of a Q form of the invariant quadratic, the O invariant quadratic form, and so you can define the odd quantum sphere. And so it is nothing but it is the object whose quantum coordinate ring is SQ modulo phi minus 1. So this property shows, so the two-sided ideal generated by this element is the same as the one-sided ideal because it's in the center. And it's easy to see that in exact analogy with the classical case, the representations UQ acts on SQ 2n minus 1 as the direct sum of L k epsilon 1 k equals 0 to infinity. So you just get the sum of all of those modules, which is exactly what happens in the classical sphere as well. So now we continue. We want an analog of SQ of the kth sum of k copies of V. But we don't just apply SQ. We use the definition in terms of tensor powers. So this is SQ of V tensor to the k. And so this is what's regarded as the quantum analog of the coordinate ring of the direct sum of k copies of V. And we have some we have some invariants which are pretty obvious. We have analogues of phi with different factors. And let me stress that when we talk about generating the algebra of invariants, we mean generating in this algebra. So this is a fairly tricky algebra. This is a twisted multiplication, so the term generated by, just as in the classical case, it has yet another twist. So let me just point out that we have elements phi ij in SQ of V, tensor to the K, invariant under UQ, which is defined as follows. So let's define X. Actually, we don't need to. So there are K copies of these. So what I do, I take this element phi applied to the I and j coordinates. Yes. So it's pretty clear. So analog. You can write down a formula for it. Analog of phi on factors I and j. Then theorem. Let me call this algebra AK. So the first statement is that AK to the UQ is generated as associative algebra by the set of phi ij over all possible values of I and j. You obviously need to take only I less than j. So it's generated as an associative algebra. And the second thing is that the phi ij satisfy relations like. Now, this should not be confused with the second fundamental theorem, because we don't know a version of the second fundamental theorem. I'll just write down one relation. This is in the simpler. These relations always in the quantum world have to take into account the relationship among the indices. So if I is less than j is less than k, that's unfortunate, is less than L. I won't change a notation now, but you have to bear in mind that this k is not the same as this k. Then phi ij, phi kl is equal to q minus q inverse times phi ik, phi jl minus phi il, phi kj. This is and there are many other relations like that. So I just want to make a couple of remarks about the proof.
So then Q is equal to 1.
Pardon?
What does that mean when Q equals 1?
When q equals 1, it means these commute because it's a commutative algebra.
Or it means that it's 0.
Yes. Yes, you can't simply put q equal to 1. Well, it's clear that you can't put. No, this is this. I'm sorry. No, this is wrong. Yeah, it should be the commutator of these two. You're right. Yeah, so you can put q equal to 1. So about the proof, how do you prove such a thing? Well, what you need to do is this algebra AK is generated by things like one tensor, and then you put a VA in there, and 1. So it's generated in algebra by these things, and this is in the ith position. You call this XIA. And you need to get a lot of relations among the XIA and the phi's. And those relations will depend on the action of the R matrix, which you can only deduce indirectly by relating its action. You know how it acts on the tensor square, so you can deduce how it actually acts on these elements. So you get a whole lot of relations among the phi ij and the x, let me say LA. And then what you do to prove surjectivity is the Reshetikin Turayev diagrams, which describe homomorphisms between different tensor powers. They span let me just say Hom K, Hom UQ K, V tensor to the to any even thing. So I'll put here V 2P. So there are relations among these Reshetikin-Turayev diagrams. For example, skein type relations that some multiple of this plus some multiple of this is equal to something like that. Well, actually, the specific one we need something like this. Well, I don't have time to go into details, but there are relations like this among these endomorphisms, which are well understood, which enables you to reduce the diagrams to a standard form. And then one needs to use relations in the algebra to show that the generators phi ij give you all the diagrams which have been put into standard form. So it's actually quite a tricky thing to relate the concept of generation in the algebra to what is known about the endomorphisms of the space. Let me make a couple of remarks about the case of GLN.
So you don't have the second one.
Pardon?
You don't have the second fundamental.
You don't have?
The second fundamental.
No, you don't have the second fundamental theorem. No. We have a lot of relations among the phi ij, but the second fundamental theorem will almost certainly involve much higher order relations than the ones we've got. And because you don't have commutativity, it's going to be quite complicated. Now, in the case of GLN, we take a basis V, V1 up to Vn, standard basis. And we form SQ of V. In this case, V tensor V is just the sum of two things. This is L epsilon 1. So this is L epsilon 1 plus L epsilon 1 plus epsilon 2. It's very easy to write down explicitly what this thing is. And one does the same thing with its dual. And then the algebra which one works in is what I call AKL. This is SQ of V, tensor to the K, tensor SQ of V, tensor to the L. V star. Now, this algebra is actually already quite well known. These algebras are actually subalgebras of UQ of GLN star. The dual space is an algebra via the operation T prime evaluated on X is the sum of T X1 T prime X2 in the Sweedler notation. So this gives an algebra structure on the dual space, and these are subalgebras of this generated by coordinate functions of the two representations V and V star. In fact, the special case, if you take K equal to L equal to N, then those two subalgebras of UQ of GLN star generate what's regarded as the quantum coordinate ring of GLN. That's what that's the algebra that Donkin works with. In this case, we have these coordinate. So we have TIA, tensor 1. This is where IA is the IA coordinate function of the representation V, and we have one tensor TJB bar. So that T is a coordinate function of UQ of GLN acting on V. This is the corresponding thing for the dual. So we call this XIA, and this is YJB. And then we have in this case psi ij, which is nothing but the sum of XIA YJA, sum over A. So this is the quantum analog of contraction on V tensor V star. And the theorem in this case, in the case of GLN, says that as you would expect, that AKL, so the UQ, is generated by the psi ij. And there are, and we know enough relations. We know enough relations to prove this, but we certainly don't have a version of the second fundamental theorem in this case either. I should say that the proof in the case of GLN is harder than in the other cases. What we actually use is some quantum version of Howe duality. And so we have some global picture of how the representation on these function spaces look, and then we specialize it. And as far as applications are concerned, I mentioned that we actually have a preprint on equivariant quantum K theory, and that's actually with a different, that's with Nagao Lam from Taiwan. And these, the results of this are are applied to the study of the Quillen higher K groups of some of the module categories that you can associate with this picture. I think my time's up, so thank you very much.
You probably can do the same for exterior powers. With the stop.
So I didn't hear.
Instead of symmetric algebras, you probably can consider exterior algebras.
Exterior, yes, absolutely. In the case of GLN, we actually use an exterior algebra as well.
Do they stop? Do they become one-dimensional?
No, they don't. The exterior, you have exterior algebras which grow as well.
They're not flat.
No.
Are these algebras of invariant flat deformations of the commutative counterparts?
Can you speak up, please?
Are the flat deformations of invariants
Are there
flat deformations?
yeah, these are, yes.
Are they quadratic?
Yes. In fact, all of these algebras are causal algebras, and they have nice duals and they have nice resolutions. We study that in the second paper.